All right, let's think a little bit about what this stuff means from a design perspective. So a core piece of this class is the design, not just the analysis of algorithms. So let's think about, suppose we had some design freedom over the various components of this recurrence. You know, by making choices about how we run our algorithm, what would we like these numbers to be? So let's focus up here just on the recurrence and ask, you know, suppose I could choose something about a, b, and f of n. What would I choose? Right. So let's think a little bit about what design choices might impact the algorithm. And first, notice that if I ever reduce a, things get better. Right. In a strict, you know, clock time standpoint, if I make a smaller by any amount, my algorithm will run faster, right? Why is this? Because a tells us how many times we branch each time we recurse. So if I look at a block of pseudocode, you can think of a as the number of recursive calls we make. If you make fewer recursive calls, keeping the rest of the stuff equal, the algorithm will run faster, right? That'll take less time. At the same time, so you know, things get better here if we make a smaller. Okay, so that's just from the standpoint of runtime. That's our fact number one. So things also get better if we make b bigger. So to see why that is, think about what happens each time we recurse. Whenever we recurse, what we're doing is processing a new problem, right? And that new problem has to be smaller than our original problem. If it isn't smaller than our original problem, then the recursion will never terminate. So the new problem has to be smaller. And what's the size of the new problem? It's this. It's n divided by b. So we're always going to be better if that's smaller. So if I increase b, that will reduce the runtime of my algorithm, as long as I can keep everything else the same while I'm reducing b. And then finally, if I reduce f of n, that'll make my algorithm run faster. Okay, so I can reduce a, I can increase b, or I can reduce the complexity of f of n, and all three of those things will reduce the literal runtime of my algorithm. Now let's compare that. Let's compare that fact. I mean, that's a fact. That's a true thing with what the master theorem tells us. So first, let's focus on the overhead dominant case, just because it's at the top of the list. And we'll say, in the overhead dominant case, what does the master theorem tell us is important? So notice that in this case, we have some complexity separation between f of n and n to the c. Okay, and n to the c is governed by b and a. Okay, and so we could ask the question, what happens to the complexity in the overhead dominant case if we change a? Right, we know that we'll reduce the algorithm's runtime if we reduce a. Right, if we make a smaller, the algorithm will run faster. But what the master theorem tells us is that a doesn't play a role here in terms of the actual the asymptotic complexity class of the algorithm. A is irrelevant because the overhead is completely running the show. Right? So what this suggests is that small changes to a and b actually don't make significant changes in the scalability of the algorithm. Right? Remember, big theta is all about scalability. It's much less about, you know, clock time, much less about runtime than it is about scalability. And if we're in this overhead dominant case, then if we have levers to pull, we better hope that those levers can reduce the complexity of f of n. Because from a design perspective, there's just not much benefit in changing a or b. So let me just write here, the main conclusion of the overhead dominant case is that a and b are not really relevant to the scalability of the algorithm. I mean, they are always going to be relevant to the runtime, right? We can always make the runtime better, but just because we make the runtime better doesn't necessarily mean that the algorithm becomes more scalable. So I'll say A, B, irrelevant. And I'm going to put irrelevant in quotes right? And if you don't watch this video and you just see irrelevant here in quotes, you might draw the wrong conclusion, because A and B they're always relevant to runtime. I'm just saying they aren't relevant in this case to the complexity, right? To the asymptotic scalability of the algorithm. If we want to make the algorithm faster in a scalable sense, we have to improve f of n, right? We can't get there by changing A and B. All right, so now let's look at the balanced case. What are the sensitivities here? What are the design sensitivities here in the balanced case? Well, what we have now is this sort of razor edge. Okay, so we'll see this even more clearly once we take a close look at the recursive dominant case. But here in the balanced case, what we're saying is the complexity of the overall algorithm is now a function of C. All right, so you can express it as a function of C. And so we could ask, what happens then if I change C? What happens if I make C better? So if I hold everything else the same, so if say I hold the f of n the same, so I don't change my recursion overhead, but I do improve something here, either by making b larger or by making a smaller, then what happens? Well, then we're not in the balanced case anymore, right? Then this no longer holds. The balanced case is a very fine-tuned place, so if I make C smaller, then I'm immediately in the case where I'm immediately moved to the overhead dominant case, right? So if I try to make this thing better by improving my recursion, then I'm in overhead dominance, and the gains kind of stop immediately. I do get a log speed up, but that's the best I can get. So basically what we think about here in the balanced case is that improving the recursion can give us at best a log speed up, right? At best, it can take us from here to here. At the same time, so that's what happens if I change A and B. I get at best a log speed up. At the same time, we could ask, what happens if I improve f of n? So what happens if I make f of n faster? Well, again, if I make f of n faster, that takes me down to this case. And what's the difference between this and this? It's a log, right? Again, a log speed up. So what we could do is we could do something like this. I could say improve A and B, log speed up. Right? So what does it mean to improve A and B? It means I'm gonna reduce A, I'm gonna increase B, and that will automatically push me into the overhead dominant case immediately, right? With any change in A and B. And in doing so, it'll give me a logarithmic speed up. At the same time, if I improve f of n, right? So if I improve f of n, question mark, I get, again, a log speed up, at most a log speed up. Right, and so kind of the takeaway here is that when we're sitting in this balanced case, the algorithm is kind of resisting our efforts to make it better. We can make it better, potentially, but this is this kind of finely tuned place where, making a change to one parameter can't make a huge change, and leaving the rest of them the same really can't make a huge change to the overall complexity. And then we're going to get a similar story down here in the recursive dominant case. So notice now in the recursive dominant case, the complexity of the algorithm only depends on A and B, right? It only depends on this critical exponent C, which is the log base B of A. So here, if we want to make improvements in the scalability of our algorithm, we have to make the recursion better. But changes in the overhead don't really make any difference, right? We've essentially made it so that we're recursion limited. We're not overhead limited. So here I can write, if I'm mirroring everything I've done before, I can say f of n is irrelevant. Again with the quotes, irrelevant. The quotes to suggest that there's a lot of nuance behind saying it's irrelevant here. Again, if I improve f of n, the running time of the algorithm will be better. but the scalability of the algorithm will not change, because here in the recursive dominant case, we are recursion limited, right? It's the A and the B that are kind of driving the asymptotic performance or the scalability performance of our algorithm.